pleasure for us to have a nice guest visitor from University of Tokyo.
Assalamu alaikum. Bugun Tokyo Universitetidan qadrli mehmonimiz tashrif buyurganlar.
His name is Professor Naoto Shiraishi.
Bu kishini familiyalari Professor Naoto Shiraishi.
He's a very young but active professor in Japan.
Bu kishi Yaponiyadagi juda yosh va faol professorlardan bittasi.
He was born in 1989.
89-yil tug'ilgan ekanlar.
No, he's already a professor. So he finished bachelor and master courses in University of Tokyo.
Bakalavriat magistraturada Tokyo Universitetida o'qiganman.
Finally, he received a PhD, Doctor of Science, in University of Tokyo in the year 2017.
2017-yilda Tokyo Universitetida doktorlik darajasini olgan, PhD qilgan.
His specialty is non-equilibrium statistical mechanics.
Sohalari equilibrium statistical
statistik mexanik
muvozanatli statistik fizika.
Title will be uploaded here. From the University of Tokyo. Today I talk about the connection between the macroscopic thermalization, macroscopic irreversibility, and microscopic quantum theory.
Men tanishtirganlardan xursandman. Men bugun sizlarga mikroskopik sekinlashish jarayonlarini, termalizatsiya jarayonlarini, makroskopik termalizatsiya jarayonlarini mikroskopik kvant fizikasi nuqtai nazaridan tushuntirishni haqida gapirib beraman.
We are now in the center of the Eurasian continent. We're here in Uzbekistan, and I came from the Far East, from Uzbekistan.
Biz hozir Yevrosiyo materialining markazida, masalan, O'zbekistonda turibmiz. Men esa juda ham sharqiy qismidan Tokiodan kelganman.
Now we are going to our main part. We first briefly discuss a typical image of the physics.
Biz hozir qisqacha fizikaning tipik rasmini ko'ramiz.
See this type of figure. The water consists of water molecules, and water molecules consist of the electron nucleus, and the nucleus consists of various quarks.
Bu yerda suv molekulalaridan iborat, suv molekulasi elektron va yadrodan iborat, yadro proton va neutronlardan va oxir-oqibatda bular quarklardan iborat.
From this type of understanding, one may be considered that if we know all about the details of the microscopic component, then we know everything.
Bundan bizaga birinchi keladigan fikr, xuddi bizlar mikroskopik komponentlarni, barcha xususiyatlarini bilsak, shunda hamma narsa haqida bilamiz degan fikr keladi.
But I'd like to ask, is it indeed true?
Men bermoqchi bo'lgan savol o'zi haqiqatan ham shunday.
So to examine this guess, we focus on this part. So the water molecule made water. This corresponding.
Bu narsani tekshirish uchun keling, mana bu qism haqida gapiraylik. Suv molekulalaridan tashkil topgan.
If our previous guess is true, then if we know all about water molecules, then we know all about water.
agar biz aytgan taklif to'g'ri bo'lib chiqadigan bo'lsa, biz suv molekulasi haqida hamma narsani bilsak, demak suv haqida ham barcha narsani bilishimiz kerak.
We want to examine this guess, and in fact, my claim is that this is not true.
Shu narsani o'z tekshiramiz, lekin men aytadigan narsa bu mumkin emas. Biz suv haqida, suv molekulasi haqida barcha narsani bilishimiz, suv haqidagi barcha narsani bilishimizga olib kelmaydi.
23 power 10 water molecules made water. Now we will see some empirical facts on water. Let us consider a tank whose left half is filled with cold water and whose right half is filled with hot water.
Bizda bir idishimiz bo'lsin. Idishimizni chap tomoni sovuq suv bilan, o'ng tomoni issiq suv bilan to'ldirilgan bo'lsin.
If we remove its separation wall, then this water will relax, summarize to water with uniform middle temperature.
Agar biz ikkala qismni ajratuvchi devorni olib tashlasak, bu suv qo'shilib bir xil bir o'rta temperaturaga kelib qoladi.
This is what we frequently observe in our daily life.
Bunaqa hodisalarni biz o'zimizning kundalik hayotimizda juda tez-tez uchratib turamiz.
On the other hand, we never observe the situation that the initial state is a uniform temperature at uniform middle temperature, and it evolves to water whose left half is cold and whose right half is hot.
Lekin biz kundalik hayotimizda biror bir tekis temperatura bilan taqsimlangan suvni bir chap qismi sovuq va o'ng qismi issiq qismga o'z-o'zidan ajralib qolishini ko'rmaymiz.
This is a well-known fact, and this is the well-known fact of macroscopic irreversibility.
Bu o'sha oldindan ma'lum bo'lgan makroskopik o'sha qaytmas jarayon hisoblanadi.
In addition, let us consider another situation that whose initial state is both cold and hot water, but its temperatures are different from the above one. But after removing its separation, it relaxes to the same uniform temperature.
Xuddi shu tajribani boshqacharoq ko'raylik. Yana bizda idishimizda sovuq va issiq suvlar bir-biridan ajratilgan va issiq va sovuq suvlarning temperaturasi tepadagidan farqli, temperaturalar farqi boshqacharoq, lekin oxir oqibatda yana avvalgi temperaturaga teng bo'lgan bitta suv bir xil temperaturali suv aralashmasini olamiz.
Then we cannot distinguish which one is initial state.
Va biz qaysi biri boshlang'ich holat ekanligini farqiga bormaymiz. Ikkala idishdagi suv ham bir xil temperaturada.
The irreversibility and this indistinguishability is established empirical fact on water.
Bu o'sha qaytmas jarayon bizda suvning ustidagi bir-biridan farqli olmaydigan hodisamizni tushuntirib beradi.
So our question is, can we derive these properties only from the property of water molecules?
Savol shuki, xuddi shu hodisani bitta suv molekulasini xususiyatlaridan tushuntirib berishning imkoniyati bormi?
In other words, there is a very clever alien who does not live in Earth, and she has never seen water, but she knows everything on water molecules. Then our question is, can she predict the following properties of water?
Tasavvur qiling, bizda yerga aloqador bo'lmagan bitta o'zga sayyoralik bor. U umrida umuman suv nimaligini ko'rmagan, lekin suv molekulasini barcha xususiyatlarini biladi. Shu o'zga sayyoralik suvlarimizdan boshlang'ich holat qaysi biri ekanligini ayta oladimi?
But recall the fact that 23 powers of 10 H2O made water, but 23 powers of 10 CO2 made carbon dioxide gas, and 23 powers of 10 complex molecules make more some complicated matter.
Endi biz ko'ryapmiz, o'nlarcha sigirma uchta suv molekulasi bir stakan suvda saqlayapti. O'nlarcha sigirma uchta karbonat angidridga molekulasi bizada karbonat angidrid ishlatadigan idishimiz tashkil qilyapti yoki biror bir tabiatdagi makromolekulamiz bizada yana bir boshqa bir moddani tashkil qilyapti. Misol bu yerda asal misolida.
But most of matters, including water, carbon dioxide, and honey, satisfy these properties. So these properties are in fact not special property for water.
Xuddi shunday ko'p molekulalardan tashkil topgan barcha sistemalarda biz ko'rib o'tgan hodisa yuz beradi. Demak, biz xulosa qilishimiz mumkin, u jarayonimiz aynan suv molekulasining o'ziga xos emas.
Therefore, it is plausible to consider that the details of water molecules are in fact not important to understand these properties.
Bu demak, xulosa qilyapmiz, bu hodisani tushunishimiz uchun suv molekulasini xususiyatlari umuman rol o'ynamasligi kerak.
So these details are in fact not important.
Demak, bu molekulaning strukturasi, shakli rol o'ynamasligi kerak, muhim emas.
So what is important? These parts, 23 powers of 10, extremely large number, is important.
Darajasi 23 juda katta molekulalar soni rol o'ynaydi berdi, muhim.
Okay. How large? 23 powers of 10. Yes.
Qanchalik katta darajasi 23 tasavvur qilishimiz kerak.
Consider the situation that we bail out the water of the sea on the earth by a paper cup. Then the number of the bailing out is 22 powers of 10. It is less than 23 powers of 10.
Tasavvur qiling, bitta darajali stakan bilan butun yer yuzidagi okeandagi suvni bo'shatmoqchisiz. Shu bo'shatishingiz uchun olib solishlar soni darajasi 22 ga teng. Hatto bu son ham darajasi 23 dan kam, kichkina.
So extremely many macroscopic components will make macroscopic universal laws.
Juda ham ko'p bo'lgan, ko'p mikroskopik komponentlardan tashkil topgan makroskopik sistemalar umumiy qonuniyatlarga bo'ysunadi.
We'd like to explain or derive this structure.
Biz hozir shu hodisa bu biz tushuntirmoqchi bo'lgan hodisa.
But before going to our main part, we put two remarks.
Asosiy tushuntirish qismiga o'tishimizdan oldin ikkita narsa haqida gapirib o'tishimiz kerak.
One is the reversibility of microscopic dynamics.
Birinchisi mikroskopik dinamikaning qayta olishi xususiyati. Qayta jarayoni.
If this dynamics of the ball exists, then its time reversal dynamics also exists.
Agar birinchi jarayon mavjud bo'lsa, vaqt bo'yicha ortga qaytish jarayoni ham albatta mavjud.
These two appear always in the form of a pair.
Bu ikkita jarayon juft ravishda doimiy birgalikda mavjud hisoblanadi.
Hence, because there exists a dynamics such that the initial state is cold and half hot, and the final state is uniform middle temperature, then there must exist its time reversal dynamics. This is a consequence of the reversibility of microscopic dynamics.
Demak, boya ko'rib o'tganimizdek, jarayon qaytariligidan sovuq suv va issiq suvning aralashmasidan o'rta temperaturali suv hosil bo'lgan bo'lsa, demak o'rta temperaturali suvdan boshlang'ich holatga vaqt bo'yicha qaytish mavjud bo'lishi kerak. Bu makroskopik sistemaning vaqt bo'yicha qaytar jarayoni ekanligi.
But we never observe the latter time reversal dynamics. So we should explain why we never observe this time reversal dynamics, although it exists.
Vaqt bo'yicha qaytish jarayon bo'lsa ham, bor bo'lsa ham, lekin biz hech qachon bu hodisani ko'rmaymiz. Shuni tushuntirib berishimiz kerak. Nega biz bu hodisani ko'rmaymiz?
Our second remark is on non-thermalizing system.
Ikkinchi gapirishimiz kerak bo'lgan narsa o'rtacha temperaturalashmaydigan sistemalar. Let me explain. Misol uchun sistemani, biror bir sistemani suvni aralashtirsak, boyagi o'rta temperaturaga keldi-ku. Bu nima? Ulardagi makroskopik kattalik, ya'ni temperatura o'rtachalashadi. Biz hozir gapirmoqchimiz, shunaqa sistemalar mavjud. Ulardagi bitta kattalik o'rtachalashmaydi. Bir-biriga ulashmaydi. Tushunarlimi? Shu haqida gapirmoqchimiz.
Let us consider extremely simple example. Many non-interacting pendulums.
Buni tushuntirish uchun juda oddiy misoldan qaraymiz. Juda ko'p bir-biri bilan ta'sirlashmaydigan matematik magnitlar.
We put the left half of pendulums in a cold situation such as a low energy, and the right half pendulums in a hot or high energy situation.
Chap tomonimizdagi matematik magnitlarimizni sovuq holatda, ya'ni kichik energiyali holatda bo'lsin va o'ng tomondagi matematik magnitlarimiz issiq holat, ya'ni yuqori energiyali holatda bo'lsin.
Then, if we leave this many body systems, then what happens? Of course, this system does not summarize.
Bu ko'p jismli sistemani o'z holiga qo'yib qo'ysak, baribir oxir oqibatda ular bir-biri bilan energiya almashmaydi, ya'ni o'z holatida qoladi.
Of course, this example is extremely simple situation, but there exists a more complicated system which appears to be interacting with each other, but in fact we can map a similar structure, non-interacting structure, and then this so that the system doesn't summarize.
Biz ko'rib o'tgan hodisa non-thermalizing sistemalarning ichida eng soddasi, ya'ni bir-biri bilan ta'sirlashmaydigan bir nechta jismlardan iborat sistema edi. Lekin bu sistemadan ham ko'ra murakkabroq bo'lgan, ya'ni jismlari bir-biri bilan ta'sirlashadi-yu, lekin o'zlarining makroskopik kattaliklari o'rtachalashmaydigan sistemalar mavjud. Kerak. Jismlar tarjimani qo'ying, e'tibor bering. Sistema bir nechta jismlardan iborat. Ular bir-biri bilan ta'sirlashadi, lekin bir-biri bilan boyagi energiya almashmaydi. Tushunaman, shunaqa sistemalar mavjud.
Famous example is integrable system. In this case, the value relates to a value, but this value is different from equilibrium value.
Bu sistemalar integral sistemalar deyiladi. Va ularni bu sistemalardagi o'rtachalashgan qiymat, ya'ni nima deydi, barqarorlashgan qiymati ularning o'rtacha qiymatiga to'g'ri kelmaydi.
Now, we first examine the structure of the state space of macroscopic system.
Makroskopik sistemani holatlar fazosini ko'rib chiqaylik.
Let us consider the situation that we throw 10,000 coins.
10,000 taqani tashlash masalasini ko'raylik.
Then the total number of cases are 10,000 power 2.
Sodir bo'lishi mumkin bo'lgan holatlar 2 darajasi 10,000 ga teng.
But if our interest is only in the ratio of the head of coins, then it must be concentrate on around 0.5.
Agar biza tangani oldi tomon tushishini ehtimolligini ko'radigan bo'lsak, bu deyarli yarimga teng.
So in almost all cases with one single trial, we can confidently predict that half is heads.
Bir marta tashlaganda oldi tomon tushishini, hodisasini kuzatadigan bo'lsak, biz ishonch bilan gapirishimiz mumkin. Tangalarning yarmi oldi tomon bilan tushdi.
And the situation is very similar to between the coin toss and water.
Suv bilan kechadigan jarayon va tanga tashlash jarayoni bir-biriga juda ham yaqin.
23 powers of 10 water molecules have possible states around 23 powers of 10 powers of 23 powers of 10.
Ön darajasi 23 ta suv molekulalari ega bo'lishi mumkin bo'lgan holatlarning soni ön darajasi 23 ning darajasi ön darajasiga ming.
What?
Okay.
Right?
Yeah. It is extremely large number.
Juda katta son.
But we can observe very few kind of observables, such as position.
Biz ko'ra oladigan narsa faqat ularning fazodagi koordinatalar.
So we find that the state structure of the state space is as follows.
Holatlar fazosi quyidagicha bo'lsin.
This circle represents all possible states of water molecules.
Bu nimamiz, doiramiz suv molekulalariga bo'lishi mumkin bo'lgan barcha holatlarni o'z ichiga oladi.
In this state space, almost all states are equilibrium or uniform temperature, as an example, and non-equilibrium states, such as non-uniform temperature, share extremely small fraction.
Bu yerda suv molekular butun holatlar fazomizdagi deyarli barcha hududlar, barcha sohalar muvozanatlashgan temperatura, barqarorlashgan temperatura holatiga to'g'ri keladi. Juda ham kichkina qismi esa, juda ham kichkina qismi barqarorlashmagan holatni ifodalaydi.
This is called typicality, which states that almost all states represent equilibrium state.
Typical degani eng ko'p uchrab turadigan narsa, ya'ni bu narsa tushuntiradi bizga eng ko'p uchrab turadigan narsa, demak barqarorlashgan temperaturalar bo'ladi.
The typicality explains why the microscopic reversibility and macroscopic irreversibility can coexist.
Mana shu typicality bizga tushuntirib beradi.
Microscopic reversibility and macroscopic irreversibility.
Bu bizga mikroskopik jarayonlar qaytarligini va makroskopik jarayon qaytmasligini tushuntirib beradi.
Our initial state is non-equilibrium or non-uniform temperature. Then it is natural to expect that this escape from non-equilibrium to equilibrium, the majority. But if our initial state is uniform temperature, then in almost all cases it will evolve to another uniform temperature state, equilibrium state.
Yes. Bizda boshlang'ich holatdagi barqarorlashmagan temperatura holati bo'ladigan bo'lsa, u holatdan shu muvozanat holatdan barqarorlashmagan holatdan keyingi holatga o'tishi qochadigan bo'lsa sistema. Bizga barqarorlashgan holatga o'tish ehtimolligi katta hisoblanadi. Lekin agar boshlang'ich holatimizda sistema barqarorlashgan temperaturada turgan bo'lsa va uni keyingi holati ham baribir yana barqarorlashgan hududga to'g'ri kelib qoladi. Tushunarli bo'ldimi?
So, microscopic reversibility and macroscopic irreversibility should be understood consistently.
Demak, mikroskopik qaytar jarayon va makroskopik qaytmas jarayon o'sha birgalikda tushunilishi mumkin.
But we remark that typicality explains that thermalization is a natural phenomenon, but this is not the proof of thermalization.
Demak, bu jarayon bizga o'sha sistemaning barqarorlashgan temperaturaga o'tishi bizga xuddi tabiiy hodisadek ko'rsa ko'rsatadi, lekin bu bizga o'sha barqarorlashgan holatga o'tishni o'zini isbotlamaydi.
In almost
Can you elaborate more
on this explanation?
Yes.
Typically, this is not a rigorous proof. This is just one argument, and not so it hold in many cases. But this is not proof, and there exist several exceptions. So, if we want to have a mathematical proof, a mathematical formulation, typically is insufficient for thermalization.
Hop, demak, unda bo'lyapti-da. Shu hozirgi biz ko'rgan jarayon bizga o'sha termalizatsiya jarayoni bo'lish kerakligini ko'rsatsa-da, lekin termalizatsiya jarayonini matematik keltirib chiqarishimiz uchun yetarli emas.
In almost all non-integral cases, the non-equilibrium initial state will relax to the majority equilibrium state.
Barcha ko'rgan holatlarimizda barqarorlashmagan holatdan keyingi muvozanatlashgan holatimiz bizda barqarorlashgan holatga to'g'ri keladi.
But in some cases, the non-equilibrium initial state remains in the non-equilibrium subspace, and this is indeed occurred in integrable systems.
Ba'zi holatlarda esa sistema o'sha barqarorlashmagan temperaturalar fazosida qolib ketadi. Mana bu faqat integrallanuvchi holatlarda yuz beradi.
Now, the problem of thermalization is divided into two parts.
Demak, termalizatsiya muammosi ikkita qismga bo'lib o'rganiladi.
First is relaxation. That is, temporal fluctuation is small.
Bu birinchisi relaksatsiya jarayoni, vaqtinchalik fluktuatsiyalar juda kichkina.
If temporal fluctuation is large, then we never say that this system thermalizes.
Agar o'sha fluktuatsiyalar juda katta bo'ladigan bo'lsa, biz bu sistema termalizatsiyalanadi deb ayta olmaymiz.
The second is the long-term average is equal to equilibrium value or not.
Keyingi aytadigan gapimiz o'sha uzoq muddatdan keyin erishiladigan o'rtacha qiymat barqarorlashgan, muvozanatlashgan holatga tengmi yoki yo'qligi.
Even if relaxation occurs, the value after relaxation may be different from equilibrium value.
Can you repeat this?
The value after relaxation may be different from equilibrium value.
Shunday holatlar bo'lishi mumkin bizda muvozanatlashgan holatdagi qiymat o'rtacha qiymatdan farqli bo'lib qolishi mumkin.
If we can prove presence of relaxation and its long-term average or the value after relaxation is equal to equilibrium value, then we succeed in proving thermalization.
Agar uzoq muddatli barqarorlashgan holat bizda o'rtacha qiymatga teng bo'ladigan bo'lsa, demak sistema termalizatsiya bo'lgan. Ya'ni sistema barqarorlashgan qiymatga o'tgan.
But before going to our main analysis, we here briefly explain quantum theory.
Asosiy tahlillarimizga o'tishdan oldin kvant nazariyasini qisqacha gapirib o'taylik.
In quantum theory, the state is represented by a vector.
Kvant nazariyada biror bir holat vektor bilan ifodalanadi.
If we write the opposite direction, then it means it's complex transposition.
Agar biz qarama-qarshi jarayonni ifodaladigan bo'lsak, bu kompleks ifodalar bilan ifodalashimiz kerak.
And observable is represented by Hermitian matrix.
Biz kuzatadigan narsalar Hermit matritsasi bilan, yes? Hermit matrix. We can observable, any observable in quantum theory is represented by Hermitian matrix. Barcha o'sha biz kuzata oladigan kataloglarimiz Hermit matritsasi bilan ifodalanadi. beriladi.
Termin tipidagi matrisalar.
Particularly, the most very important observer is Hamiltonian A, which is observable for energy.
Biz kuzatadigan makroskopik eng muhim kataloglardan bittasi energiyani beradigan funksiya bo'lib, bu Hamiltonian hisoblanadi.
If state H is observable and this is a state of vector and En is a value and this relation holds, then we say that En is eigenenergy and the corresponding state is energy eigenstate.
Hamiltonian funksiyasini funksiyasiga ta'sir etadigan bizda bu yerda xususiy holatlarga to'g'ri keladigan xususiy qiymatlarni olamiz sizlarga.
If you've already learned linear algebra, this is the same as the eigenvalue equation.
Agar sizlar o'sha chiziqlar algebrani o'tgan bo'lsangiz, o'sha xususiy qiymatlar tenglamasi bilan bir xil.
Then, if we expand any initial state by using this energy eigenstate as this.
Biza barcha o'sha holatlarni o'sha xususiy qiymatlar bilan yozib chiqishimiz mumkin. Xususiy qiymatlarga to'g'ri keladigan funksiyalar bilan xususiy funksiyalarning yig'indisi bilan yozib chiqishimiz mumkin.
Then the time evolution of this initial state with this Hamiltonian is given as this.
Vaqt bo'yicha o'zgaruvchi funksiyamiz esa quyidagi ko'rinishda ifodalangan.
This is a state at time 0 and this is a state at time t.
Birinchisi psi nolimiz vaqt 0 holatdagi holatimiz, psi timiz t vaqtdagi holatimizga to'g'ri keladi.
This is Heisenberg picture.
Heisenberg equation.
Schrödinger equation.
No. Schrödinger
equation.
So,
and the important part from this expression is that the absolute value of each quotient is unchanged and only the phase changes.
Bu yerda eng muhim narsa barcha xususiy funksiyalarimizning absolut qiymatlari, ya'ni koeffitsentlari o'zgarmaydi. Bir xil qiymatga ega.
So you are confining to the system where Hamiltonian is time independent.
Yes. We need to remember that throughout this talk we consider the situation that Hamiltonian is time independent. The system is isolated and we do not do any operation.
Biz ko'rayotgan barcha holatlarda Hamiltonian vaqt bo'yicha mustaqil, vaqtdan mustaqil. Harakatga bog'liq emas.
So the time evolution of the quantum state is schematically understood as this. So this is a complex plane and real and imaginary. The question, the angle rotates with different angular speed, angular velocity.
Vaqt bo'yicha o'zgaruvchi holatlarimizni grafik jihatdan quyidagicha kompleks fazada tasvirlashimiz mumkin. Bular haqiqiy qiymatlar, bular kompleks fazo. Faqatgina ularni bu har bir funksiyalarimiz burchak tezliklar bilan farq qiladi.
energiyalar haqida tushib boradi energiyalar.
Now we go back to the problem of thermalization.
Biza o'sha thermalizatsiya muammosiga qaytaylik.
So for us to read the problem of relaxation.
Hop, relaksatsiyani ko'rib o'taylik.
Our quick answer why relaxation occurs is due to the dephasing.
Formula xatomi? Bo'yicha summa bor-ku, ana tepadan kelib qolgan, mana bu kompleks funksiyasi bo'lgan. Summa xatomi?
This I represents the order I, the function I.
Function I. Yes, this is complex imaginary. I'm sorry, this is very confusing notation. I'm sorry.
Yeah, no problem, sir. Hop, demak, nima uchun o'sha relaksatsiya hodisasi nima qilish kerak? So'zib bo'lish kerak. Relaksatsiya bo'lishining sababi bu nima? Defazalash. Ya'ni fazalari o'zgarishi. Bu funksiyalarning fazalari o'zgarib borishi bizga relaksatsiyaga olib keladi oxir-oqibatda.
Asosiy faydaga shu bo'lib kerak.
If the phase is synchronized in the initial state, but after time evolution, they become unsynchronized.
Boshlang'ich holatda fazalar sinxronlashtirilgan bo'lsa, ma'lum bir vaqt o'tgandan keyin fazalar qanaqadir nosinxronlashgan holatga kelib qoladi, tartibsiz bo'lib qoladi.
Professor, so I'm sorry to cut you. Does it mean that when we multiply by this factor en, somehow the vectors change unequally? I mean, we are actually with a Hamiltonian with this matrix. So the effect of this matrix on eigenstates is different depending on the eigenstate.
Depending on eigen value. You say that the number, the quotient Ci is different.
Yes, because of
yes.
Hamiltonian acts on them differently because of it.
Yes, Ci is both Ci and En. I'm sorry. This must be n.
No, as I understand.
Sorry. And then these values all different among eigenstates, but we can discuss the phase. So in fact, in this picture, this is a slightly different meaning, but the essence is the same. So the length of the arrows are different. So this means that the Cn is different between different states.
Tarjima qiladi.
Let us.
One more. So energy eigenvalue. Okay, arbitrary pair of energy eigenvalue should be irrational.
Yes.
Synchronization.
Yes, I implicitly assume this.
O'sha energetik zotlarni o'sha xususiy holatlar irratsional bo'lishi kerak.
Let us see how a dephasing occurs in a very simple example.
O'sha defazalash jarayoni qanday sodir bo'lishini bitta oddiy misolda ko'rib o'taylik.
We consider a sum of 5 different sine curves.
Beshta turli sinus funksiyalarini kombinatsiyasini ko'rib o'taylik.
Also, it coherent, it synchronized at the initial time, but later it will appear to relax.
Boshlang'ich holatda sistema koherent, sinxronlashgan sistema bo'lsa, vaqt o'tishi bilan bu sistema desinxronlashgan.
You can see why this occurs by plotting these 5 sine curves in the same graph as this.
Bu qanday hosil bo'lganini ko'rish uchun 5 ta alohida funksiyalarni bitta grafikda tasvirlab ko'rsa bo'ladi.
These 5 sine curves are synchronized at the initial time, but later it appears very different. It's very different.
Va boshida bu 5 ta funksiyamiz sinxronlashgan bo'ladi. Vaqt o'tishi bilan juda ham fazalari o'zgarib boradi. Defazalash jarayoni.
Of course, because 5 is very small number, the wave quickly shows recurrence. But by taking a more larger number, then the relaxation continues longer time.
Biz hozir tanlayotgan funksiyalarning soni 5 ta va kam nomer bo'lgani uchun sistema juda qisqa vaqtda bizda qaytib sinxronlashadi. Agar shu qo'shayotgan funksiyalarimizning soni ortishi bilan relaksatsiya jarayoni uzoqroq vaqt sodir bo'laveradi.
So, if many energy eigenstates are used in the initial state, then the phases tend to unsynchronize. So, with such initial state, the system is expected to relax.
Agar biz juda ham ko'p bo'lgan xususiy qiymatlarni oladigan bo'lsak, siz faza bizda sinxronlikdan qochishga harakat qiladi va natijada sistema relaksatsiyalanadi.
this guess is mathematically justified in a rigorous manner. This theorem is proved.
Bu odsani matematik jihatdan quyidagi teorema bilan tushuntirsa bo'ladi.
Temporal fluctuation observable is bounded from above by the inverse of effective dimension. Here, effective dimension is roughly equal to the effective number of energy eigenstates used in the interstate.
Is temporal fluctuation of observables
Yes.
is bounded by this effective dimension, right? O'sha biz kuzata oladigan makroskopik kattaliklarimiz yuqoridan chegaralangan effektiv o'lcham bilan chegaralangan va bu effektiv o'lcham bizada boshlang'ich holatdagi xususiy holatlarning effektiv soni. Tushuntiradi. Effektiv o'lcham boshlang'ich holatdagi xususiy holatlarning effektiv soni hisoblanadi. Bu bizada kattaliklarning fluktuatsiyasi xuddi shu bilan chegaralangan tepada. Boyagi 5 tada bizada tezroq sinxronlashdi, 19 tada relaksatsiya nimasi vaqti uzoqroq davom etdi. Tushunarlimi?
Unfortunately, so if the effective dimension diverges in the summative limit, the temporal fluctuation vanishes. So relaxation is proved.
Agar effektiv o'lcham bizada termodinamik chegarada uzoqlashuvchi bo'lsa, bu son, ya'ni kattalashib o'sib borsa, bizada fluktuatsiya yo'qolib boradi. Demak, sistema relaksatsiya.
Fortunately, under physical initial state, the effective dimension is shown to diverge in both numerically and analytically.
Bu o'sha effektiv o'lchamni uzoqlashuvchi ekanligi ham raqamli hisob-kitoblarda ham analitik jihatdan isbotlangan, ko'rsatilgan.
But we should remark that this result holds both integral system and non-integral system. So both summarizing system and non-summarizing, some of non-summarizing systems.
Bu hodisa ham integrallanuvchi sistemalarga ham, integrallanib bo'lmaydigan sistemalarga ham qo'llasa bo'ladi. Demak, bu narsani ham termalizatsiya bo'ladigan sistemalarga ham, termalizatsiya bo'lmaydigan sistemalarga ham o'rnli bo'ladi, qo'llasa bo'ladi.
Integral systems also show relaxation, but the value after relaxation is different from the equilibrium value.
Integrallanuvchi sistemalarda bu barqarorlashish jarayoni ham yuz beradi. Faqat bu yerdagi bizadagi relaksatsiyaga uchragandagi bizadagi qiymat sistemaning o'rtacha qiymatlaridan farq qiladi.
What is the definition of integral system or integrability?
I do not put the definition. I think I've already explained it yesterday. Because the definition of quantum integrability is very arguable and very highly the subject of debate, and there is no single definition. But one definition is that if we can solve in a particular manner, we can solve the quantum system, the energy eigenstate of this system, then we say that this system is integrable. Another definition is that if the system has infinitely many local conserved quantities, then we say that this system is integrable.
Men integrallanuvchi sistema va integrallanmaydigan sistemalarga boshida aytmadim. Men kecha aytib bo'ldim deb o'yladim. Kvant fizikasida integrallanuvchi sistemalar va integrallanmaydigan sistemalar ta'riflari bahsli masala hisoblanadi. Juda ko'p faktorlarga bog'liq. Lekin umumiy qilib, sodda qilib aytadigan bo'lsak, agar boshlang'ich kvant holatni ifodalovchi o'zgaruvchilar o'sha xususiy holatlar soni kam bo'lsa va uni hisoblashning imkoniyati bo'lsa, sistemani biz integrallanuvchi deymiz. agar boshlang'ich holatni ifodalovchi xususiy holatlarning soni juda ko'p bo'ladigan bo'lsa, biz buni integrallanmaydigan sistema deymiz.
But the definition of integrable is not important in my talk. Please just understand that integrable system is a typical example of non-thermalizing many-body system.
Bu mana integrallanuvchi sistemani tarifi biz hozir ko'rayotgan ishimizda muhim emas. Shu narsani qabul qilinglar. Demak, integrallanuvchi sistema bu termalizatsiya bo'lmaydigan sistemadir.
But okay, in summary, the problem of relaxation is almost clarified.
Umuman olganda relaksatsiya muammosi deyarli tushuntirdik.
So we next.
Because of the quantities are concerned, the integrable system can return to itself. Because of most of the quantities are concerned, the entropy change to itself will not be so much because of it will return to itself.
You say recurrence. So, but recurrence occurs in both integral and non-integral systems if we weigh experience.
But I mean, for integrable system,
As far as I understand your explanation, integrable system, the system does not go out from its non-integrable state. In reversible state, you can just, a system goes out from this system, this space, and comes again. As Professor explained, if you can wait extremely long time, then the occurrence of this any state is probable.
because it's easy.
Maybe you can take the quiz session to the end. Maybe it's better to ask the question at the end.
But maybe it is better to ask at the end of my talk. Maybe it is not so many much. Okay, now we move to our second part. This problem is much harder than problem of relaxation.
İkinci masalamızga o'tamiz. Bu masala relaksatsiya masalasidan ancha qiyinroq.
Some theories explain some thermalization of some non-integral systems, but not all thermalization phenomena is explained by a single theory. If we restrict the very specific system, the thermalization of specific system can be explained by some theory, but there is no general theory.
Termalizatsiya jarayoni aniq bir xususiy bir nazariyalar bilan tushuntirib beriladi, lekin termalizatsiya jarayonini umuman ta'riflaydigan umumiy nazariya yo'q.
I'd like to ask, is there any general theory of thermalization?
Men sizlarga bermoqchi bo'lgan savol, umumiy qonun bormi termalizatsiya jarayonini tushuntirib beradi?
We take a very simplified setup to consider the general problem.
Umumiy muammoni nima qilishda, muhokama qilishda juda bir oddiy misolni oldim.
We consider a one-dimensional system and its Hamiltonian is shift invariant and it interacts only with nearest limits.
Bitta chiziqli sistemani oldik. Buni nimasi Hamiltoniani barcha sohalarda invariant va faqat yondosh sohalar bilan bir-biri bilan tasvirlashadi. Bir-biriga yaqin nimalar qismlar sistemada tasvirlashadi xolos.
Shifting means the translation or invariant.
Yes, translator invariant, shift invariant are the same. I think I use this in the same meaning.
Hozir ana kvant mexanikasi bilan elektrodinamikani o'tgansizlar, o'zgarishdagi invariantlik bilan xuddi shunaqa sistemani ko'ryapmiz.
The observable A is a shift sum of one body observable.
Kuzatiluvchi macroscopic bizada bir jismli kuzatuvchini integral makroskopik kattaligida
And in furthermore, we restrict that the initial state is a product state of a state on a single site.
Demak, bizlar bu holatimizda boshlang'ich holat, yakka holatdagi holatni funksiyasi.
Okay. And we ask that consider the following problem. The initial state is a given one and evolves according to the Hamiltonian age. Then is there is a long-term average A is close to the equilibrium value or far from equilibrium value?
Quyidagi masalani ko'rib o'taylik. Bizda boshlang'ich holat Hamiltonian operator bilan o'zgarib boradi, tasvir o'zgarib boradi. Shunda uzoq muddatli bizda erishiladigan vaqtimiz va holatimiz bizda barqarorlashgan holatga to'g'ri keladimi? Yo'q. O'sha barqarorlashgan holatimizdagi A ning qiymati o'rtacha A ning qiymatiga to'g'ri keladimi yoki yo'q?
This is, I think, the one most simplest setup in the field of quantum thermalization.
Bu o'sha kvant thermalizatsiyadagi eng sodda masala hisoblanadi.
But recently, I and my collaborator succeeded in proving that in this program, is this simplest setup is still undecidable. So, it is proven that we never prove the presence absence of thermalization.
Bu yaqinda men va meni hamkasbim quyidagi narsani isbotladik. Bizda kvant termalizatsiyada hech qachon bu hodisani qaysi bir bo'lishini ayta olmas ekan.
This is not that the effort of physicists is insufficient, but that it is from the summarization is never solved from a mathematical fundamental reason.
Bu fiziklar kerakli energiyani berib, keraklicha o'zini masalani yechishga kirishmayotganidan emas. Bu shunchaki termalizatsiya matematik jihatdan ko'rsatib bo'ladigan hodisa emasligidan.
Because to explain our result, we need some terminology of computational theory, so we briefly explain the computational theory.
Biza raqamli nazariyani o'zi bir ishlatamiz terminlarni, shu uchun bir ikkita terminlarni ko'rib o'taylik shu raqamli nazariya. Hisobli nazariya desak ham bo'ladi.
We consider decision problem. We consider decision problem, which is a problem can be answered in yes or no, yes or no.
Biz qaror qabul qilish masalasini ko'raylik. Bunda javob ha yoki yo'q bo'ladi.
If there exists a procedure or an algorithm which always answers yes or no correctly for all inputs, then this decision problem is called decidable.
Agar shunday muammo bo'ladigan bo'lsa va shu muammoni kirishda har doim shu muammodan keyingi oladigan javobimiz aniq bo'lsa yoki ha yoki yo'q bo'lsa, bu qaror qabul qilsa bo'ladigan sistema deyiladi.
There are many examples of decidable decision problems.
Bu qaror qabul qilsa bo'ladigan masalalarga juda ko'p misollar keltirsak bo'ladi.
Or if we can prove this problem in the form of theorem, of course this problem is decidable. If we can solve this decision problem in the form of a mathematical theorem, then this problem is obviously decidable.
Demak, matematik teoremdan nazardan biror muammo hal qilib bilsak, demak o'sha muammo bizda qaror qabul qilsa bo'ladigan muammo hisoblanadi.
In addition, combinatorial optimization problem, which is practically very hard problem, but we can solve combinatorial optimization problem by a brute force method by taking a exponentially long but finite time. so computer optimization program is decidable.
Yana ham murakkabroq sistemani ko'rsak, ya'ni kombinatorial optimizatsiya nomosini ko'radigan bo'lsak, bu murakkab sistema bir nechta nima deydi, funksiyalarimizdan iborat bo'ladi, lekin uzoq vaqt kutadigan bo'lsak, oxir oqibatda baribir bizga ha yoki yo'q javobini beradi. Bu ham qaror qabul qilsa bo'ladigan muammolarga kiradi.
If the problem is not decidable, so if there is no procedure or algorithm which always answering yes or no correctly for all inputs, then this decision problem is called undecidable.
Agar bizada muammoda oxirida ha yoki yo'q javobini oladigan hech qanday algoritm bo'lmaydigan bo'lsa, bu muammolar qaror qabul qilib bo'lmaydigan muammolar deyiladi.
Of course, if the problem is undecidable, we never solve this problem in the form of a theorem.
Bunday turdagi muammolarni nazariy jihatdan yoki teorema jihatidan umuman hal qilib bo'lmaydi.
We present one famous example of undecidable problem, Turing halting problem.
Biz bitta mashhur qaror qabul qilib bo'lmaydigan masalani ko'rib o'tamiz.
In this problem, the input is a program for a computer or a universal Turing machine.
Bu yerda inputimiz shu masalada inputni bilasizlar-ku, dasturni biladi matematiklar. Hamma fiziklar. Inputimiz bu yerda bizda kompyuter uchun dastur, universal Turing machine.
Universal Turing machine is roughly equivalent to a computer which can perform any computation.
Bu universal Turing mashinasi har qanday hisob-kitoblarni bajara oladigan nima?
And the problem is to decide whether this computer with this program halts at some time or does not halt and runs forever. We should distinguish these two.
Biza narsaga qaror qabul qilishimiz kerak. Masala shundan iborat, qaror qabul qilishimiz kerak. Bu nima? Dasturimiz ma'lum bir vaqtda to'xtab qoladimi yoki cheksiz vaqt ishlayveradimi?
Turing proves that this problem is undecidable.
Bu nimamiz, mashinamiz bizga ko'rsatyapti. Bu muammo qaror qabul qilib bo'lmaydigan muammo.
We here remark that we cannot solve the halting problem by just running this computer with this program.
Biz bu muammoni shunchaki kompyuterga o'sha ishlab chiqqan dasturimizni tashlab kutib o'tirib yecha olmaymiz.
In case of halting, yeah, we can confirm that it halts.
Agar kompyuter to'xtab qolsa, demak biz aytishimiz mumkin, ha, demak to'xtaydi. Ishlashdan to'xtab qoladi.
But if in the case of non-halting, then we cannot distinguish this computer does not halt forever and or this computer halts but after extremely long time, for example 1 year or 10 years or whatever.
Agar o'sha dasturimizda kompyuter ishlab tushib turadigan bo'lsa, biz qaror qabul qila olmay qolamiz, ya'ni ajrata olmaymiz ikkita opsiyani. Bu kompyuter shu dasturni ishlashdan hech qachon to'xtamaydi yoki juda ham uzoq vaqtdan keyin to'xtaydi degan masalani qo'llaymiz.
So just running the computer does not solve a halting problem.
Shunchaki kompyuterni ishlatib ko'rish dastur bilan bizada o'sha kompyuter dasturni ishlatishdan to'xtaydi yoki to'xtamaslik masalasini hal qilib bermaydi.
Okay, now we go back to the problem of thermalization.
Yaxshi, endi yana thermalizatsiya masalasiga qaytaylik.
Our key lemma is this part. The thermalization phenomena can emulate all possible computational tasks with yes/no output.
Demak, lemma kiritamiz bu yerga. Shunaqa lemmamiz bor. Bizda termalizatsiya jarayoni barcha nima oxirida ha yoki yo'q degan javobni beradigan hisob-kitobli masalalar. Aytolmayman. Qisqasi termalizatsiya jarayoni decidable problem.
We can construct an elaborated quantum manifold system such that its dynamics emulate the computational process in computers. we can construct elaborated quantum measurable systems such that its dynamics emulate the computational process in a computer or Turing machine.
Quant ko'pchilik sistemada bu hisob kitobli masala bo'ladi.
So, for any program, there exists a proper Hamiltonian, proper measurable system such that this system, quantum system, summarizes if and only if the corresponding universal Turing machine with a program holds.
So if the program holds, then the system does not thermalize?
So there exists a correspondence with the program and system, and we such that this program, if this holds, then this system summarizes. We can construct such kind of case.
Demak, boyagi ko'rib o'tgan sistemamiz bilan termalizatsiya jarayonini o'xshatsak bo'ladi. Bu o'xshatish shunday. Ya'ni boyagi nima desaydagi programda agar programmaning dasturning to'xtashi bizaga sistemaning termalizatsiya bo'lishini beradi.
The key idea is that if a Turing machine holds, then a kind of switch turns on and the system starts summarization.
Bizada shunday bo'lib qolsin, asosiy narsamiz. Agar dastur ishlashdan to'xtasa, bizada termalizatsiya bo'ldi deb chiqadi.
So, if we can decide whether summarization occurs or not, then we can decide whether a corresponding Turing machine with corresponding program holds or not.
Yana keyin boyagi nimaga keldik, xalqqa keldik. Termalizatsiya bo'ladimi yoki yo'q degan savolga boyagi dasturni kompyuterga yuklaganimizda kompyuter ishlashdan to'xtaydimi yoki yo'qmi degan masala.
But we know that Turing machine, the holding program is undecided contradiction.
Demak biz bilamiz boyagi masaladan bu dasturda kompyuter ishlash to'xtaydi degan masala bu qaror qabul qilib bo'lmaydigan masala.
So the assumption we can decide whether summarization occurs or not is false. So we cannot decide whether summarization occurs.
Demak, boyagi kiritgan masalamiz ikkalasi bir-birini qarama-qarshi qilib qoldi. Birinchi aytgan gapimiz bor edi, termalizatsiya faqat decidable sistemalarda bo'lish kerak edi. Keyin orqa tomondan keldikda termalizatsiya bo'ladimi yoki yo'q degan masalaga programma to'xtaydimi yoki yo'qmi degan masalaga ekvivalent bo'lib qoldi va oxir oqibatda bizdan olgan natijamiz termalizatsiya bo'ladimi yoki yo'qmi umuman aytib bo'lmaydi.
One may feel that this result is negative.
Va bu natijamiz manfiy.
But this result implies not only the undecidability of summarization, but also that the summarization solves any computational task.
Bu manfiy natijamiz faqat termalizatsiya muammosi. Can you explain?
So summarization, this result implies that not only the undecidability of summarization, but that summarization phenomena can solve any computational task in a kind of form.
Demak, bu natija bizga beradi. Termalizatsiya jarayoni faqatgina hal qilib bo'lmaydigan masala emas. Termalizatsiya jarayoni har qanday hisob kitobli masalalarni hal qilish ekanligi.
Although one may think that summarization is a very simple phenomenon, but in fact it is as complex as all possible computational process.
Demak, bizdan xulosa qilyapmiz. Termalizatsiya jarayoni juda ham oddiy narsadek ko'rinsa ham, lekin barcha hisoblash jarayonlariga o'xshagan o'ta murakkab hodisadir.
We shall explain one very intriguing example application.
Biz siz bilan odamning kayfiyatini ko'taradigan bitta shu narsani tatbiq masalasini ko'ramiz.
to explain this, we introduce Riemann hypothesis. Details are not important. This is a conjecture on prime, which is still unsolved at present and is listed in the Millennium Program.
Bu muammo o'sha Riemann gipotezasi muammosi bilan keladi, ya'ni o'sha top nimalarda to'psonlar masalasi bor-ku, formulasi. O'sha tushuntiriladi. Bu yechilmagan nima, ming yillik masalalar qatoridan bittasi.
Now, it is known that there exists a program such that it holds if and only if the Riemann hypothesis is false.
Agar Riemann gipotezasi yolg'on bo'ladigan bo'lsa, nima, o'sha boyagi faraziy nimamiz dasturimizni kompyuter ishlashdan to'xtash kerak.
So, by applying our construction to this program, we find that there exists a one-dimensional quantum system which summarizes if and only if the Riemann hypothesis is false.
Natijada bizda shunday xulosa kelyapti. Bir o'lchamli shunday kvant sistemasi bor. Bu sistema termalizatsiya bo'ladi qachonki Riemann gipotezasi yolg'on bo'lsa.
Of course, we remark that at present we do not know that Riemann hypothesis is true or false, but we can write down this Hamilton.
Hozirgi vaqtda biz o'sha Riemann gipotezasi rost yoki yolg'onligini bilmaymiz, lekin o'sha Hamilton funksiyasini biz yozamiz.
Okay, this is summary of my talk. Thank you for this.
Shular barchasi meni aytadigandan xulosasi edi. E'tiborlaringiz uchun rahmat.
Riemann
You can just give a little information about.
Briefly, details are completely non-important. So Riemann hypothesis, just important point is that we have a program. First is the unsolved one. If anything is solved, this statement is trivial. And the second is that we have a program to examine the Riemann hypothesis true or not. This is important. Others are not important. So this is just an very famous unsolved problem in mathematics. The genius Riemann cannot solve this problem. And many other genius mathematicians fail to solve this problem at present.
Hozir ustoz so'rablar, o'sha Riemann gipotezasi haqida bir qisqacha ma'lumot berib o'ting deb. Bu kishi aytdilar, u Riemann gipotezasining o'zi aslida nimaligini hozir muhim emas. Shu muhim narsa bizda Riemann gipotezasining rost yoki yolg'onligi hali isbotlanmagan, lekin shu narsani nima deydi, keltirib chiqara oladigan biz funksiyani yoza olamiz, raqamli masalani hal qila olamiz hozirgi holatimizda. Shu muhim deb aytdi. Va oxirgi qismida aytgan gaplari, bu problema shunchalik nimaki, yechib bo'lmaydiganki, o'sha juda ham bir nima deydi, kuchli olim Riemannni o'zi ham yecha olmagan.
Gather some question, maybe someone has question.
Savollaringiz bo'lsa beringlar.
Thank you for the presentation. My name is Bobashar. I am a student of Naoto Shiraishi University. So basically, you say that the thermalization is connected to the solving problem and solvable problems, right? And mathematically, we can prove that there is a set of problems that can be modeled computationally. Because if you try to merge the classic set theory and the pigeonhole principle, you come up with the idea that there are some problems that cannot be solved using computers. So does that mean that thermalization process cannot be modeled in a computer at any time? Because if you are able to model the thermalization process into a computer, it already means that you can solve all the computational problems, right? But theoretically, we already proved that there are a set of problems that you can never solve using computers.
This depends on what is the meaning of modeling. For example, let us consider the case of the Turing's halting problem. Of course, this is a very undecided problem, but we can run this program with this input. So the whole details of the dynamics, the computational process is fully tracked traced by a computer, but we cannot decide whether what happened after maybe after a very long time. But this is and then we can so. But we can in this case we can emulate each step of computation in the case of faulting problem. So a similar thing is, I think, similar thing is hard for thermalization phenomena. We can perform a computer simulation in your laptop in step by step, but or maybe at our larger size. But we cannot compute infinite long time in a computer. This is the difference. So. What is the meaning of the modeling is highly depend. The answer depends on what is the modeling.
Yeah. So by modeling, I mean like compatibility.
Yes.
The problems. By modeling, I mean the.
Uzruk transfer.
Okay. Bu kishi savol berdilar. Siz aytingiz termalizatsiya muammosi hal qilib bo'lmaydi deb. Lekin kompyuterda modellashtirish mumkin, gamma funksiyasini yozib dedingiz. Shuni o'zi demak masalani hal qilib bo'ladi degan emasmi? Biz funksiyasini yoza olyapmiz, kompyuterda esa kodini yoza olyapmizmi? Demak, hal qilib bo'ladigan masala-ku degan savol berdim.
Naobrat teskari qarang. Termalizatsiya proses bu, ya'ni agar termalizatsiya muammosi yechilsa, hamma computational muammolar, ya'ni hisobda muammolar yechiladi. Computer science point-dan olib qaraydigan bo'lsak, shunaqa hisobda muammolar borki, ular kompyuterlar bilan yechib bo'lmaydi. Buni oddiy to'plamlar nazariyasi bilan keyin pigeonhole principle, directly principle. Directly principle ikkalasini birlashtirsak, shunaqa nazariyaga kelib chiqadiki, ya'ni bu countable infinite cheksizliklarning turlari, sanasi bo'ladigan cheksizlik, sanalmaydigan cheksizlik ikkalasi bir-biriga to'g'ri kelib va natijada bizning xulosamiz shunaqa bo'ladiki, shunaqa muammolar bor, ularni kompyuterlar bilan yechib bo'lmaydi. Bet aytilishi bo'yicha, demak, agar biz termalizatsiyani kompyuterga agar termalizatsiyani yechib olsak, hamma muammoga yechim topa olamiz. O'sha xulosa qilsa bo'ladimi? Ya'ni biz allaqachon bilamiz hamma muammoga yechim topamiz. O'shani xulosa qilish mumkin, ya'ni termalizatsiyani hech qachon modellashtira olmaymiz. Hech qachon o'sha prosesda to'liq modellashtira olmaymiz.
Savollarni tushunmadim.
Yo'q, bu o'sha shunaqa
Sizda savol yo'q edi. Javoblarni ham tarjima berasiz?
Yo'q, bu prosta men qiziqqan savol, ya'ni o'shan o'zi proof bo'ladi, ya'ni termalizatsiya bu qachondir kelajakda ham modellashtirsa bo'ladigan narsa emas, ya'ni buni hech qachon modellash iloji yo'q.
Kompyuter nuqtai nazaridan buni iloji yo'q, lekin shuni modellashtirish cheksizlikka bog'liqmi yo'qmi deb savol beradi. Hozirgi nuqtai nazariga bu aytayotgan teoriyasiga to'g'ri kelmaydigan bir ikkita xulosalar mavjud. Ana shu xulosalardan siz hozirgi vaqtda foydalana olasizmi, yo'qmi? Yo bo'lmasa kelajakda foydalanishingiz mumkinmi? So'rayapman. Shunchaki oddiyroq tushuntiring. Ko'pchilik hozir savolingizni nimaga bog'liq jihatini topolmayapman.
He mentioned about the original computer, just like kind of a problem and at the same time